So thank you for the introduction. Thank you everybody for being here again after the break. So I'll try to keep it short and focused because we are a bit late. This presentation, now we will have 3 presentations which are more or less related. So I will put with mine some basis. I'll try to keep it very basic because I want to explain how some concepts that can be seen as very complicated are actually very, very simple. So I'd like to show you how simple it can be to put a definition about connectivity that can be used in practice with some, of course, also some limitations that we will try to show you in the next 3 presentations. So the first problem when we talk about brain connectivity is the definition. We have seen in the first presentations and in the very nice introduction that several possible definitions are there for connectivity, and so we need to agree about what we are talking about, otherwise we will be talking about different things. We will get results that are difficult to compare or to give an interpretation. So talking about causality, I find that this definition, which was introduced in a paper or which was formalized in a paper by some of the speakers that are here today, is very clear and very nice to understand what we are talking about. So when we talk about causality, we can talk about a physical influence between 2 parts of a system, meaning that if something happens in a part of the systems, this will have a consequence in another part of the system. This is a very nice definition. It can be called the true causality because we make perturbation in a part of the system and we see what happens. There's a problem with this, which is we have to perturb the system. So if this is good to study probably how different brain regions are related, are linked, but it poses some problems when we want to study some brain functions because we are not observing the system, we are modifying the way it works. So a second possible approach is there, which is based on the assumption that if something causes something else, there's a temporal relation. So the cause should precede its consequence. With this approach, it's completely observational. We do not need to perturb the system. We just look the data and what they have to say. So this is what we will be focusing in this talk. And the temporal precedence can be explored by testing if there is an improvement in predictive capacity between 2 or more than 2 distinct neural events. So the first definition of what can be called causality in the statistical sense was provided in 1956 by Wiener. And according to this, this is a very straightforward definition. Just have a look at it together. According to Wiener, if we have 2 simultaneously measured signals, so the 2 signals are there, they are recorded simultaneously, if we can improve the prediction of one of the 2 time series by introducing into this prediction the information about the past of the second time series, and if this introduction of the past of the 1 time series into the prediction of the first one improves the prediction, then there must be some kind of causal relationship or some kind of relationship between the 2 that can be called causality in the statistical sense. So we don't need okay, of course we need some kind of exchange of information, but even if it's not a direct one, we can have an improvement in understanding some phenomena by introducing the information about the past of another phenomenon. So the temporal precedence is there. What is lacking here is a model that we can use to measure this. The model was introduced by this guy. This slide is not mine. I borrowed it from Daniele Marinazzo, so the full credits go to him, but I like this slide so much that I couldn't resist. I should use it, because this is how a Nobel laureate can look Look at this guy, how cool he was, unfortunately, because he passed away some years ago. So this is Clive Granger, Nobel laureate in 2003 in economy, because this tool was developed, this theory was developed in a totally different field, which was economy. And Granger took Wiener's definition and put a model in it. And the model he chose is probably the simplest that we can have. It's a linear autoregressive modeling. So according to what was later called Granger causality, if we can put into an autoregressive modeling of a time series the information about the past, so the past samples of a second time series, and this improves the prediction, which means this reduces the prediction error, then we have applied Wiener's definition to a model, which is, as I said, possibly the simplest model that we can have to this purpose. So an important point in this definition is related to directionality. We are talking about directionality because we are using, like in this example here, we are using an autoregressive modeling of time series B, which means essentially we are using a linear combination of the past samples of B itself to predict the current sample of B, and of course we will have a prediction error here, which is the residual of the model. Then we can build a second model, including, again, the past samples of B, but also a linear combination of the past samples of a second time series A, which we want to explore if it can have some kind of influence on B. And we have a second model with a second residual, which is a second different or not, it depends, prediction error here. So we are exploring the influence directed from A to B by means of these two models. If we want to explore the influence directed from B to A, we use two completely different models. So the two directions, the two influences from B to A and from A to B are separate into completely different models, and so we can explore not only directionality but also bidirectional influences and interactions between the two time series. So this is the strong point about this method. So what if we want to apply this method? The simplest way is to follow the definition. So we have the two time series, we build a univariate modeling, for instance, of X based on X's past, and the bivariate modeling of X, including also the past about a second time series way. And then we compare the residuals of the models to see if there has been an improvement in the prediction. How do we do that? We can take the variances of the residuals of the prediction errors and we can compare them in this formula here, in this index. This is the Granger causality index. What can happen? We can have basically two possible alternatives. Either there is no improvement in the prediction when we introduce the information about the past of the second time series. So if we go back to the model here, we introduce the information about way here, but this does not reduce the residual, does not improve the prediction. So the residual is close to what it used to be in the univariate modeling. This ratio here is close to 1, and so the index is close to 0, no causality. Or we can have an improvement. So we introduce these samples here in the model. This implies that something interesting is happening here. Some parameters, which are the weights in the model here, are different from 0. And this is reflected by a reduction in the residual, which means by an improvement of the prediction. And so when we look at this ratio here, it's greater than 1, and so the index is increasing. More and more different from 0 as much as the two variances are different. The third situation in which there is an increase of the residual when we introduce the information about the past samples of the second time series should not be there, because by introducing more information we shouldn't have a worse model, unless we make some mistakes in the modeling. So if we are doing a good modeling, we shouldn't have an improvement, an increase in these residuals, and so we could just have it keeping as it was in the univariate modeling or reduced by the information we introduced in the model. So very simple, very powerful index that can provide a measure of the existence of the Wiener-Granger causality or causality in the Wiener-Granger sense, and there's also some testing that can be done to see if this is significant. I will go into details later about this. And there is directionality, and also bidirectional influences can be detected with a very simple model. The only assumption we must do to use this model is the stationarity of the data, at least in the large sense, in the window we are observing to build a model. EEG and MEG, by the way, are signals that are usually quite good for this kind of modeling, provided that we have this stationarity that I mentioned. The main problem, so this is very simple, very straightforward, yet powerful, but it has a major, not drawback, but a major point that must be kept in mind, which was provided by Granger himself in 1980. This sentence is taken from one of his papers, and Granger said that true causality can only be assessed if the set of two time series that we are using in our modeling, in our definition, contain all possible relevant information and sources of activities for the problem. So that's the main problem, because usually we don't have all the information about our problem for EEG or for the brain kept in just two time series. Usually it's more than two. So what happens if, for instance, there are three? Let's give a couple of approaches that are possible in this situation. For instance, we have 5 time series. We want to apply the Wiener-Granger definition to this data set. The first approach that we can have is the so-called pairwise. So we take all possible pairs in our data set, we apply the definition to all the pairs, we build a pattern like the one in this picture. We can do that. It has been done a lot in the literature. What's the problem? The problem is what Granger said in 1980. Each time we apply the definition, all the possible sources of information must be there. Otherwise, we are doing something wrong. And this is an example of what can happen. Let's imagine that we have a connectivity like this in this pattern here. So we have one source influencing other two sources with different delays, with the same delay. We can discuss about it. In both cases, we have some problems. Let's imagine that the delays are different. What happens when we apply a pairwise approach? When we look at 3 and 1 and 3 and 2, we can find easily this kind of relationship here, but what happens when we apply our definition to 1 and 2? When we focus on this model, bivariate model. Our model, with the information that it has, which is just related to time series 1 and 2, will detect some kind of correlation between those two time series. There can be a delay between those two. If, for instance, the influence directed from 3 to 1 has a different delay with respect to the influence directed from 3 to 2. Finally, any bivariate approach based on time lag can detect a connectivity which is not there. This is not true connectivity, not true causality. So finally, the short message is when we apply bivariate approaches to multivariate data, we can obtain a lot of false positives as a result. This is a big problem because false positives are undetectable, are indistinguishable from the true causality that we can get from this method. So to avoid this, we need to feed the model with more information. We have the information from a multivariate data set. We can use it all together to build a unique model and by what is called a multivariate approach. So we can exploit the full multivariate information we have from simultaneously recorded data, and we can build a model which is a bit more complex, not in principle, but in terms of how many parameters we have, but which is much more precise. Because if we go back to the same example, once we feed the model with all the information coming simultaneously from the 3 time series, the model is able to understand what is due to a true influence directed from the 3rd region to the other 2 ones, or what is not there. So the false positive problem is greatly reduced when we use a multivariate approach. Of course, we can still have problems if there are some sources which we are not able to put into the model. So the problem is not entirely solved, but all the information we have, we can use it. We don't lose the opportunity to improve the accuracy of our results by using all the information we have. So the first message is that multivariate approach can greatly reduce the amount of false positives that you can have from this kind of connectivity analysis, of causality analysis. How do we build such more complex, as I said, not in principle, but in terms of parameters, number of parameters model? We just start from, again, the autoregressive modeling, and we introduce into the model all the possible interactions between the time series. So if you look at this model here, if you're not familiar with it, it may appear a lot more complicated than the 2 models that we have seen in the previous slides. But if you look at it more closely, you will see that it's essentially the same model. What we do here is to model each and any time series in our dataset as a linear combination of the past samples of the time series itself and all the other time series in our dataset. So in principle, it's exactly what we have done with the bivariate approach. Now, how can we extend the Wiener-Granger's definition to a multivariate condition? If we just look at the residuals, like it was in the original definition, we can do something like this. We can compare 2 models again. We are not comparing anymore the univariate and the bivariate model. We are now taking the full model, including the target time series and all the other time series. Here in this example, I took just 3 of them, just for the sake of simplicity, but it can be as long as you want, the data set. We build the multivariate modeling, and we have a residual, which is a measure of the accuracy in the linear prediction that we perform. Then we remove 1 time series from the modeling. We keep all the rest, and we look at the residuals again. We compare them. Once we have removed just 1 time series, the reduction in the residual, which is due to the introduction of that time series, can be attributed to that source. So again, like we did with the Granger test, we compare the residuals, and they can have comparable variances, or the variance can be reduced by the information we introduced into the model. And again, this can be a measure of what happened in terms of improvement in the predictability of 1 time series thanks to the other time series. With this definition, we are still focusing on the model residuals, but the model is very interesting in its structure, and we are in some way neglecting some interesting information that is there in the parameters. So what are the parameters of a multivariate autoregressive modeling? If we look at them in a scheme like this, for instance, we can look at those parameters as weights that measure in some way the influence of each sample of the source time series directed to the target time series with a specific time lag delay. So we have a parameter for each pair of time series, for each direction, and for each lag. So we have a lot of information which is there into the parameters. If we just look at the residuals, we lose some interesting information. So different models, different methods were developed based on parameters, or on parameters and residuals together. Most of them are defined in the frequency domain, and I will focus on the frequency domain, which is particularly interesting for the EEG and MEG analysis, which are the focus of this course. So to look at those parameters in the frequency domain, we just need to provide a frequency version of the model, which means transforming the time series, but also the parameters. So the parameters, if you look at them as vectors in time, they can be transformed by Fourier transformation, and they can be seen as functions of frequency, like in this example here. In a multivariate approach, we will have a matrix of functions of frequency, and each function of frequency will be a transfer function linking a specific. If you look at this like a filter with n inputs and n outputs, if we have a data set made of n time series, each function here is a transfer function linking a specific input with a specific output of our filter. You can look at this filter in two ways, as a predictor or as a generator. So you will have two matrices which are closely related to each other. They are both transfer matrices of the filter, and in particular, if we make an inversion of this matrix that we get by transforming the parameters, we have a transfer matrix which is strictly related to the spectral matrix of our dataset. So this is closely related to the spectral matrix of our dataset, which is at the basis of different measures like coherence and so on. So when we focus on the parameters instead than on the residuals, we have more information, because the information is again, it's related to a specific pair of time series. It can be read from column to rows. So for instance, this function here relates the nth input to the first output, so the nth region or the n node to the first node. So there's a direction. This is in principle different from this one. This matrix is non-symmetrical, so direction is still there. The information about directionality is still there, and we have a distribution in the frequency domain of this influence directed between the two time series. Several measures were developed based on this. Just to follow the timeline of their appearance, directive transfer function was introduced in 1991. Partial directed coherence was introduced in 2001. Sorry. Okay, the only difference between those two measures is the matrix they are based on. So the partial directed coherence is based on the A matrix, which is the direct transformation of the parameters. The DTF, the directed transfer function, is based on the H matrix, which is the matrix we obtain by inversion of the A matrix. There are some similarities, also some important differences between those two measures, which I'm not going into detail, but if you're interested, we can discuss them later. In principle, this is something quite important. Instead, different normalizations are available. Normalizations are important because they give meaning to the numbers we find by those estimators. Normalization is probably the major drawback we have so far when using these measures, because no normalization is perfect. They change the numbers we get for connectivity, and so the interpretation that we can give to those numbers. What they don't change is the existence or not of a connection, especially when using, as I will show you in a few slides, a statistical approach for validation, which is invariant with respect to normalization. So normalization is not a problem when talking about the structure of the network. It can be a problem when talking about the values, the strength of the connection. So, as I said, statistical assessment is an important point. What has been done for years is using to build surrogate distributions by means of shuffling procedures. Recently, an asymptotic statistic was introduced with the advantage of reducing significantly the time required by this assessment. So from days, weeks to minutes, maybe hours, it depends on the amount of data you have, so a significant reduction with an accuracy which is still very, very high, and it's also invariant with respect to normalization, as I said. So it's very important to adopt the correct the correct statistical assessment procedure, otherwise it has been demonstrated that you can get interesting results even from random data. So this is a point which I'd like to stress. And the last point I'd like to stress is the assumption of stationarity of the data. As I said, stationarity of the data is required for this kind of modeling. Our data are usually not stationary or not often stationary. So what can we do when our data are not stationary? Different approaches are there, luckily. We can adopt a short time window approach. So especially if we have multiple trials, we can take short time windows in which our data are approximately stationary, and we can use this sliding window approach to overcome the limitation or the hypothesis of stationarity, or other approaches based on adaptive modeling, for instance, based on recursive least squares or on a general linear common filter, are available to overcome this hypothesis. And this is an example of result you can get when you use an adaptive approach, for instance. So finally you get a time frequency distribution of causality, which can be analyzed in different ways. So this is an example for a specific pair of regions in the brain, and you can see how connectivity is distributed at different frequencies during the experiment. Then you can do whatever you want. You can look at it in time. You can make snapshots or movies of how the network changes in time. You can extract some parameters based, for instance, on graph theory, and you can track what happens in connectivity network, like in this example. So motor task, time varying network, time varying properties of the network, which can be tracked in time. There's an important point to be kept in mind when dealing with this kind of data, when there's a stimulus which is related to ERPs, which can be seen as perturbation that can have negative effects on connectivity. So I'm not going into detail for time, because we are running out of time, but you will find this reference in the material you will have, so you can focus on this, or you can learn more about this. But there's a problem related to event-related potential cell-Granger causality that needs to be addressed when dealing with stimulus-based. So this is my final slide. There have been recently a lot of discussion about what procedures can alter the correlation between data that can result in false positives or false negatives in EEG. This is true. This does not mean that we can avoid pre-processing. The message is that we must be aware of what we are doing when doing pre-processing on our data, and we must be sure that we are not throwing the baby with the water. So we need to remove some kind of correlation which is spurious, but we must not throw the baby away with the water. There are issues related to volume conduction, which will be addressed by the next speakers' talks. And when moving to the source space, especially, we also need models which can increase their dimension significantly, which is also a problem, but there are some tools to deal with that. For instance, the general linear common filter is a way to deal with measures that can be, with models that can have a high number of parameters. Other approaches are also there. I will skip the applications, but there's a mini symposium on that on Thursday morning, if you are interested in, and you will find in the material some suggestions from possible publicly available toolboxes for this kind of analysis. I would like to acknowledge people which we collaborate around the world, and you all for your kind attention. And now I leave the place to the next speaker, who is Daniele Marinazzo, which will show you some personal view, but very general, in my opinion, about different measures that you can use for EEG and MEG connectivity.